Welcome back. Today we're going to be talking about a new form of bonding, covalent bonding. We're going to be comparing it to how it relates to ionic bonding. And we're going to be talking about how these molecules can be formed utilizing Lewis dot structures. Okay, so if we're trying to recap here, so chemical bonds, once again, these are the things the forces that hold together atoms, and it basically gives us the ability to make molecules. And we have two categories. We have the ionic bond category. These are bonds that are formed between ions, the positively and negatively charged species. So these are between metals and nonmetals. And today we're going to be talking about covalent bonding, and that's formed between two nonmetals. And so we're talking about bonds that occur in this area. So carbon-carbon, nitrogen-nitrogen, sulfur-carbon, fluorine-chlorine. Any of these combinations are going to generate a covalent bond. And the difference between the covalent and ionic bond is that we are now sharing electrons as opposed to simply gaining or losing electrons or stealing electrons. So we can see in the above example that, of course, chlorine is taking an electron, it's gaining an electron, and sodium is losing one, and as a result they're actually formally getting charged, and these atoms are kind of glued together because of it. In covalent bonding, though, we get a different kind of system here, in that we have the nucleus, and we have our electron clouds, and these electron clouds are kind of overlapping, and that we seem to be kind of sharing electrons between the two nuclei. I think one of the very first things that we should kind of talk about or point out when it comes to covalent bonds is that covalent bonds form discrete molecules. So when we were looking at ionic systems, we would form Na plus and Cl minus, and that would kind of repeat over and over and over again. And even though we had the empirical formula of NaCl, we knew that there was a billion sodiums and a billion chlorides. They were just kind of repeating in all different directions, and that's what made the salt. So with covalent bonds, however, we have these discrete small molecules, and so when we're talking about the molecule caffeine for instance in coffee, we're talking about this one right here. And this molecule has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens, and that's it. That is the whole kit and caboodle. If we want to look at something like amphetamine is another molecule that is composed entirely of nonmetals to nonmetals. We would kind of just basically count up all of the atoms, and that would give us our molecular formula. So we would have 6 carbons, 7, 8, 9. So we have C9, we have 9 carbons, and we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 hydrogens, and it looks like we have a single nitrogen. And so the chemical structure of amphetamine, whether it's on the street in Chicago or made in Bangladesh, it doesn't make any difference. It's still C9H13N. Okay, so how do you make covalent bonds, right? So you have perhaps these two non-metals, maybe a carbon and a fluorine, and once again, just like with ionic systems, everything is happening from the valence electrons, from the outer shell electrons. And so we're gonna use Lewis dot symbols to once again know and kind of guide us with how many electrons we have to work with. And so if we have carbon here, carbon's first shell is full, first orbit is full, energy level is full, but its second one is not. And so carbon has got these 4 valence electrons that it can bond with, and if we look at fluorine, fluorine also has its first energy level that's full, but it has 7 electrons in its valence. Okay, so the thing about non-metal bonding is that they really can't do ionic bonding, and we're going to use Cl2, chlorine gas, as an example. And so first what I'm going to do is I'm going to go ahead and I'm going to draw out the 2 chlorines that would form bonds, and what we're going to do is we're going to have a make-believe hypothetical scenario where we perform basically what would happen in an ionic bonding situation. And that is to say that maybe this chlorine atom steals an electron, right? It steals it. And so in this scenario, what we would get is we would get one super duper happy Cl minus, and this one would have all 8 of its electrons. But what would we get over here? We would get a really crappy scenario. We would actually get the Cl plus, and the Cl plus now has 6 electrons, so it's even worse off than it was. It's even farther away from its goal than it originally was. And this is really the case of what happens all the time when you're dealing with elements on the same side of the periodic table, is that there's no nice way to steal electrons. That someone wins and someone loses. Both aren't happy. And so the solution to this is going to be sharing electrons. And so we can kind of see that example down here, and we can see what happens. So if we take this chlorine and this chlorine, both of which want 1 electron, and we actually just bring them close together, what we can do is we can form a new bond where they both are sharing the 2 electrons. So they each bring 1 to the party, and together they have enough so that they both have their octets. So what we can do is we actually can think about this chlorine atom has all 8 of its electrons, and in fact that chlorine atom also has all 8 of its electrons if you count the sharing, the shared pair of electrons. One of the things we should do, though, now is that we have different types of electrons. So we have bonding pair of electrons. These are the electrons that are being shared right now. They are important in making sure everyone has a satisfied octet. But we also have these non-bonding or lone pair electrons. And these can also be quite important, but they're not directly involved in creating a bond between 2 different atoms. Okay, so let's look at some happy molecules, and let's go across the period 2 elements, so carbon, nitrogen, oxygen, and fluorine. We're obviously not going to go to neon. Neon has its complete octet, so it's not going to engage in any kind of this bonding. But we can look, and we look at the valence electrons that these elements have. So carbon has 4, and so carbon likes to make 4 bonds so that it can be happy. So let's make 4 covalent bonds, each of which will share 2 electrons, giving it its 8 valence electrons. So let's kind of maybe off to the side here draw what that might look like. And so we could draw something like this. Okay, so the carbon is bringing 4 electrons there, and hydrogen, which has only a single electron, is going to bring 1. Right? There's going to be 4 of these guys. Now, one confusing thing for a lot of people is that everything really strives to have an octet around it. Everything, of course, that is except hydrogen. Hydrogen exists with that in that first energy shell that can only support 2 electrons total. And so if hydrogen happens to have 2 electrons around it, a duet instead of an octet, it's actually quite happy. Hydrogen can't support any more electrons than that. So let's keep going across the second period there, looking at nitrogen. One of the nice things about Lewis dot structures is that actually, as you go across a period, all you have to do is you have to keep adding up the electrons. So carbon has 4 valence electrons, and if we go to the next element, nitrogen has 5. And so what we're going to do is we're just going to keep walking around the circle, and you can see right there that what I've done is now nitrogen has 3 electrons that it can bond with, and it has 1 lone pair. Let's keep doing that example here. 1, 2, 3, 4. Oxygen has 6 total. 5, 6. So you can see oxygen has 2 lone pairs, 2 sets of electrons that are not going to be bonding, and 2 that are. And if we go one more, 1, 2, 3, 4, 5, 6, 7, we get fluorine, and fluorine has 3 sets of lone pairs and 1 bonding. And so when we make bonds with these molecules, for nitrogen to get its octet, we can combine this with, for instance, maybe 3 hydrogen atoms, and this is going to get us something that looks like this. This is ammonia. I'm actually just going to draw in these with straight lines. And you can see here we have one non-bonding lone pair, and then we have three bonding pairs. So to make oxygen happy, in this case, we only have the necessary for 2 bonds, and so it doesn't have to be hydrogen, but we're going to do that for this case. And here we go, and this is going to make what we know as water. Now we see that water has a pair of lone pairs on it. So here are lone pairs, and then we also have our 2 bonding pairs. And then finally we can get HF, so this is, it only needs 1 electron to give the 8 octets. And this is hydrofluoric acid. This is a pretty strong acid. You can see here it has 1 bonding pair of electrons, and it has these 3 sets of lone pairs. There are some instances where atoms will form, or they'll share more than just 2 electrons. They're going to form more than 1 bond. And they're doing this because in the end, atoms want to get an octet. They want 8 electrons around itself. And so a great example might this be O2, right? The gas that we're breathing right now. And so if you look at the structure of oxygen, the Lewis dot structure, you can see it has 2 bonding electrons out of its 6 valence electrons, and so it can share these in a whole bunch of different ways, but it can share them with itself, and it can share not 2 electrons, or it can share not a total of 2 electrons, but a total of 4 electrons to form what is basically a multiple bond or a double bond. So this is a double bond right here. And as before, it does this because in this case you can see you can have the 8 electrons that are being shared. Whoa. And we have another 8 electrons right there that are also being shared.